definitely the starting point here would be classical field theory. So we start with not field theory, but classical mechanics. And classical mechanics tells us that there are a finite number of degrees of freedom or finite number of generalized coordinates, q sub I. Well, q can be anything actually. It can be x, y, z, whatever. It's just a general system of coordinates. And we label each coordinate with q sub I of t, which means you have a spatial coordinate q and a specific time t. Then in classical field theory, the objects of interest are fields denoted with a phi, which is basically a functional of the position and time. So essentially, what x was before in classical mechanics was a coordinate in space has become just a label to label fields, right? So essentially, x has been relegated to being just a number. It's nothing more special than just a number that is basically inside your more fundamental field. And this leads, because we're defining a field for every point in space, this leads to an infinite number of degrees of freedom because space is infinite. So fields are described by equations as well, just as particles. Anything we want to make sets of, we write an equation down for it. And the equations are most easily formulated in the classical mechanics realm by using Lagrange's formulation of classical mechanics, which has to deal with energies. We know of Newton's laws of motion. Those are vector equations that come out. Vectors are not very easy to work with. However, in Lagrange's formulation, we use energy, and energy is a scalar, and scalars don't have any direction, so to say. So those are easier quantities to work with. So if you want to work out the field equations of motion, then you go towards the first step to Lagrangian mechanics. The classic example would be E equal to this complicated expression, complicated looking, it's not really complicated. This is nothing but the electric field that we work in electrodynamics. And connected field is, of course, the magnetic field, which is denoted by, which is just defined by a term of A, with the minus sign. This is a magnetic field. And if you plug these expressions in for E and B into, and use A nu to be this 4 vector, which has 0th component phi, which is scalar potential, and you have a vector potential A, the 3 component. And this basically is a 4 component field, A nu. And in this formulation, if you plug in expressions for A here, this into these 2 expressions, and then plug in those expressions in Maxwell's equations, you see that these expressions of E and B satisfy Maxwell's equations. So these are the first starting points of examples that you meet in classical mechanics: electric field and magnetic field, which describes the dynamics of the electric field and the magnetic field. All right, so let's review Lagrangian formalism for a little bit. Lagrangian is defined as follows. Quite simply, it's the difference in energy. So T here is the kinetic energy, U is the potential energy, T minus U is the quantity we are calling L, which is the Lagrangian. And the Lagrangian happens to be a function of the coordinate Q, the time derivative of the coordinate Q dot. So dot just means dq dt, and T is also a variable that L depends on. So T is kinetic energy, as I said, U is potential energy, and that is Lagrangian for classical mechanics. But what happens in classical field theory? Well, the Lagrangian becomes basically a function null, because remember, phi is a function of position and time. So you have a function of a function, which is a functional, right? So the Lagrangian becomes functional of the field and its derivatives, okay? And this curly L, you integrate over all of space, you get the total Lagrangian. So this curly L is then called the Lagrangian density. But really, we don't really differentiate between L and stripped L. We just use this and call it the Lagrangian, because, we're not mathematicians. We want to make the math as easy as possible. So this stripped L will often, I will never call it Lagrangian density. I'll just call it Lagrange. I will abuse notation a lot during these talks. as is practice. All right. Now, we can also define another quantity, which is the classical action. And this is coming from this expression, right? So S is the time interval of the Lagrangian. So you take this quantity and you integrate this whole thing with time, you get the action. In space time, really, this x and t are not separate, but it's coded in this 4 integral, d4 x. So x has 4 components, remember, x0 is time, that is going to be d0x will be dt, and d3x will be dx, dy, dc, right? So this is the classical action. This is a quantity that is the definition of the classical action denoted with the capital X. And turns out that this S, classical action, is Lorentz invariant. What does that mean? Well, if you put it into the Lorentz transformation machine, it spits out exactly the same thing, right? All right. Now, the fundamental building block of classical mechanics and field theories is the action principle. What does that mean? So you look at this. So we're actually going to classical mechanics. So space and time can be separate for a minute. So essentially, a particle starts at initial time t0 and goes to some final time t1, and you can choose. The particle is free to choose any path. So essentially, an infinite number of choice. You can choose any 2 point, any 2 curve that you like to go between x0 to x1. However, Haskell action principle tells me that whatever path you choose, the path you actually choose has to be the minimum action path. So basically, the path that minimizes the action is the one that particles choose to follow. So that means minimizing the action means whenever we're talking about minimums and maximus, we're talking about derivatives going to 0, right? So basically any change going to 0. So this action principle tells me that delta S go to 0, right? So that means any change in the action must be no change at all. It is 0, right? It's minimized. And basically you take the action expression right here and plug it in, and you take the derivative of derivative with respect to what? With respect to phi and with respect to d mu phi, right? And you do this complicated looking integral. It's not really complicated, trust me, but it looks a hell of a lot complicated. It's a lot of things to unpack in this early morning. So I see everyone got a cup of coffee. That's good, because you got to see a lot of equations, and you may fall asleep. I don't mind. I also fall asleep sometimes during lecture. That's okay. Just be awake for the important part. All right. Now, where do we go from there? Well, if you do it in thinking with your coffee by your side, you see, okay, this may come out of a product rule. Product rule of what? Well, basically, if you take the derivative of the product of dl d mu phi with this change, and you expand that out in a product rule, you can manipulate this term very well. So what we do exactly that, and we manipulate that term. This left-hand side is 0, right? So that is fine. And basically, this term gives out 2 terms. Because remember, product rule, uv is a multiplication of 2 functions, and then you take the derivative. First time you take the derivative, the first function stays the same, the second function changes, then you add it to the second function, stays the same, the first function changes, stuff like that. When you do that, you get 2 terms, right? So basically, this term gets replaced by 2 terms. One of them is here, and the other one is this piece right here. Now, this piece is really unimportant. Why? Because, well, what is del phi? Del is a small change in the function, right? Small change in field. So small change in field, meaning all it really cares about is where it started and where it ended. Where it started and ended at fixed location. I want whatever path I choose, I can only go between a fixed initial and a fixed ending point. So basically, the endpoints are fixed. That means the total derivative of this change of my endpoint is going to be 0. So we call these terms surface terms. And circuit terms in field theory are often set to 0 because of that reason. Because of essentially keeping 2 endpoints fixed. All right. So basically, if you want to take the derivative of this term, goes to 0. Okay. So this term is 0. That's good. That means we have simple expression, which is this remaining part, right? So we have the action interval, d4x of this thing, and you have a change in the feeling. And this part right here turns out to be 0 because this whole thing must be 0. This is arbitrary and this is not definitely not 0. If you integrate it over space, you get infinity. So the only thing that really can be 0 is this term. So this term being 0 returns your Euler-Lagrange equation of motion. Okay? So remember this. This is the Euler-Lagrange equation, and you will use it everywhere in field theory. Okay. All right. Now, does anyone know what this is? Huh? No. Yeah. Okay, good. So people know who any Euler. And I don't know if you've noticed, it's quite amazing. The quite shameful as well. That's so far down the line in this talk, we have only mentioned one female scientist, one female physicist. That's not good, right? And you know why that is? Because in those days in Europe, women were not allowed to get a higher education, right? And some would say that things are still pretty difficult for women in science, right? So she and others like Marie Curie and Minerva Maric, they kind of pushed the boundaries of physics and like put in important contributions. So without Emmy Noether, as Einstein puts it, physics would be terribly incomplete. So just imagine if like women had the opportunities to do more in science, what could have been achieved, right? So it's always good to think about it and then expand out our horizons, make things a little bit more accountable for everyone. Okay? So this is Emmy Noether. She was a Jewish mathematician, and Emmy Noether has a very important contribution in the field of physics. That is, basically, she proved that every continuous symmetry of the Lagrangian returns a conserved current, which identifies as J mu, right? And the equations of motion then becomes a continuity equation. So this invariant looking thing goes to 0. If you expand it out in terms of the 0, 0, and 3 components, you get this kind of an equation. This is the continuity equation. So what this actually means that if you have a continuous symmetry of the Lagrangian, let's unpack that statement. What is a symmetry? Well, a symmetry means if you change something in fundamental about the Lagrangian remains unchanged. Right? If you try to change something, that change really doesn't change the Lagrangian. That's the symmetry of the Lagrangian. If you have a continuous symmetry, Noether's theorem tells me that you end up with a conserved quantity. Okay? And conserved quantities are integral part of nature, right? An integral part of physics. From the very beginning, you have learned about one conserved quantity, which is from elementary school, energy, right? Energy conservation, momentum conservation. These all come from this simple but yet profound statement by Emmy Noether. So this is Noether's theorem. And this is where conservation laws come from. All right. So in classical mechanics, you remember what is if you have symmetry under spatial translation, that means you move from this point to that point and nothing really changes. The equations of motion are unchanged. And what is the conserved current? Or what is the conserved quantity? If you want to be very basic about it. Spatial translation, momentum, right? So the momentum remains unchanged. That's conservation of momentum. Whatever momentum you started with, when you are not moving, you end up with the same momentum that you end with when you're in a moving frame. And what about time translation? So if what if you're moving time and not in space, that gives rise to the other conserved quantity that everyone lost, that is energy. Okay? So this is where Noether's theorem plays an integral part in developing physics from the very beginning, right? And in field theory, we see that if you change the space-time coordinate, x nu, and you shift it by some number, e nu, the field kind of shifts as a total derivative. So field shifts like a change of the derivative of the field tagged along with this number, right? So then if you plug this into your Lagrangian, the Lagrangian also changes like this total derivative. So basically the old Lagrangian stays but has an extra terminal. The extra term happens to be the derivative of the Lagrangian. We call this a total derivative. And invoking Nether's theorem, we see that if you want to change the Lagrangian, basically as a small change in the Lagrangian, you can derive this equation. Basically, you change the equation of motion and you get this quantity. This thing simplifies to this quantity, TU. And this T mu nu is basically going to give you a continuity equation. And this T mu nu is very fundamental. And I'm sure this will be talked about in Maxwell's vectors and also Rapin's lecture. This is where your energy momentum tensor comes in. So for spatial translation, so remember space-time kind of merges space and time together. So this translation is actually a translation in space, is also a translation in time. So this means it gives rise to two conserved quantities, momentum and energy. So the zeroth component of this T mu nu is energy. And the spatial component of this T mu nu is the total momentum of the field. Right? So the derivations are, these are the big pictures. The derivations are, you take a whole course in quantity, there is still can't know everything. So I'm skipping over those steps. All right. Now, the next important part is, okay, like we have a equation that we want to find for the scalar field. So what is a scalar field? A scalar, in terms of Lorentz transformation, is something that doesn't change under Lorentz transformation. So this is the Lorentz transformation machine again. Let's say you place a number 2 inside the Lorentz transformation machine, it spits out 2 exactly. Doesn't do anything. All right. So you take something in, you spit something out exactly identical to the one if you get. So that's scalar quantity. So a scalar field is a field you put it in the Lorentz transformation machine, doesn't do anything to it. All right. So that's a scalar. So we want to find the equation for the scalar field. So we start off with a scalar field denoted by a phi of xt. And okay, one notation thing, this should essentially have a arrow on top, but usually we write it as phi of x only, because in space time, x and t are kind of merged, right? But I missed an arrow. Lorentz invariant. So phi is a scalar, means it's Lorentz invariant, it doesn't change under Lorentz transformations. So under our Lorentz transformation, phi goes to a pi, doesn't do anything, right? And we know that space-time coordinates change according to this relationship. We have seen that at the end of the last lecture. Basically, you invoke a Lorentz transformation vectors in front of the space-time coordinate. There's a new vector would give you then the transformed vector, right? So the x mu change in different frames. The definition changes in different frames, but actually the space-time point itself is not going to change. It's remain stakes. And for a real scalar field, real means, you just have no complexity involved. You just have real components of the field. And for a real scalar field, the Lagrangian is this. Okay, how do I get? Well, let's say I hand it. All right. So I hand you this Lagrangian. You have this Lagrangian for scalar field. Now let's analyze the term. What are these different terms? Well, this is nothing but, what is it? This term, what do you think it is? This is a derivative of phi. This is the derivative of phi. What are derivatives really? You will also have like time derivatives as space derivatives. What is time derivative? Kinetic energy. Right? So basically you have the product of two derivative terms. That's a kinetic term. Okay. So this term here is a kinetic term. Okay. Remember kinetic energy won't have mv squared. So this is where the p comes from. V squared comes from two derivatives. Right. And then you have 1 hat m squared phi. What is that? Well, looks like some kind of potential energy, right? So it depends on the spatial distribution of phi. So this is a potential energy term, but if you want to really simplify things, what you can do is you can think about the master scalar field. So this parameter m here, you may think it is mass. It may be mass. It may not be mass. It's just a parameter at this point. So you can set this parameter to 0 if you want to really simplify things. But let's keep it. Let's keep this m where it is. And let's say, okay, we can think of it as mass term. It doesn't have to be more complicated things. All right. So this is the kinetic energy. This is the potential energy. And we get the Lagrange. Right. Now we want to work out Euler-Lagrange's equation. Those are the equations of motion that will describe field. How will we do that? Remember your Euler-Lagrange equation. It has two terms. First, take the derivative of the Lagrangian with respect to the puke, I. And then the second term is you take the Lagrangian, the change in the Lagrangian and again change it, right? With respect to the time. And so this is the first term. You change the Lagrangian with respect to phi. You get, look at the Lagrangian, what do you get? The only phi dependent term there is this one. You take the derivative, very simple, right? It's just going to be 2 comes out, divides out the 2, you get -1 and m squared times phi. So everyone has done tensor mathematics here. Right? So tensor calculus, you have successfully done, right? You give yourself a pat on the back. And then the second term for the Lagrange equation is this little piece right here. Basically, you first change the Lagrangian, you take the change in the Lagrangian with respect to the derivatives, and then you could change it again with respect to del mu, right? So what does this look like? Well, this term doesn't depend on the derivatives. So this term can be accepted or back L mentioned. So this term has a lot of derivatives in it. So this is probably the important term in this piece right here. Okay, so now let's separate out the two. The only term that I really need to plug it to this L is this first term. This second term, you can understand, doesn't depend on the derivatives. So that inside 0. All right, now, you're taking the derivative with respect to partial mu phi out, mu downstairs. So you look at it, you think, okay, then this is the term that I'm taking the derivative with respect to. So you get onto one term, 1/2 g mu nu, partial mu phi, right? But that's not going to happen because really there are two derivatives and you have to consider both of these terms. Okay. So this mu nu indices must be considered both in this derivative. So let's separate it out. So first you get the usual one, right? So you take the derivative with respect to du phi, this goes to 1, you have this remaining. Everyone good with that? Good? Everyone alive? Well, heartbeats? Jet? Okay, good. And then you have the second term as well. The second term is you take the derivative with respect to nu. But there you go, a mu here and a mu here. And my math physics students, you know what this is? This is just going to be the Kronecker delta. You take two derivatives with different indices, it gives you the Kronecker delta, right? So what does the Kronecker delta mean? Well, the Kronecker delta tells me that this term will be 0 whenever mu and nu are not equal. So then the only term that remains is nu and nu are equal. So basically, you can set either like this one to just mu, right? And so this one was only u, right? Or only nu, whichever one you like. So this sets what you choose, the index, and then you contract out the g mu news with the partials. So this term gives you the news contract out, you get partial mu right here. Then news sum over, we say, or contracts. We can also say that. And this term right here, let's say first you contract the mu's, you're left with the nu, but then this sets nu is equal to mu, so you can again place any mu here. So this is different. So you can easily have two terms. So this is just one. Then you take the derivative del nu downstairs and del nu upstairs. So this is the kinetic term. And sorry, this is the little piece of the equation of motion here. So now we are in place to really write our Lagrange equations, which is going to be signified with a box. The box is equivalent to the Laplacian in force space-time. So the Laplacian is a nebula, the inverted delta, and this inverted delta becomes a box when you talk about space-time together. All right, then you have the equations of motion. Basically, this minus that equals 0. So this minus that equals 0, or you can factor out the negative signs. I can do it and write it in a very nice manner. Right? Box plus m squared phi x equals. So that's a very elegant equation, and this describes what we call the scalar field. Okay. All right. Okay. So this was elementary, but still, if you have a question. Down, up. Okay. Yes. Cool. I have to rehash your question for everyone though. Yeah, it's not very, very interpretation, but I relate where you go. Oh, sorry. Oh, So basically, when you move in space-time, you're actually moving both in space and in time. So if you move this way, you're not only moving this way, but this is a shear transformation. You move kind of in space-time, the space-time spreads out. So essentially, when you're talking about space-time kinetic energy, you have to incorporate both of the okay? So because it's a shear transformation, it's not just a transform. Right, good. Okay, keep it alive. All right. Now, let's move on then. Now, the another important formulation of classical mechanics. So, all of these different formulations, we start with Newton when you're in nursery, and then you pass all the kind. You get older, you come to university. People talk about Lagrangian, and then they also talk about Hamiltonian. But why do we need all these different formalisms? Because Newtonian mechanics is hell of a lot complicated. We can always think about, okay, I noticed from the very beginning of my life, like I was born and that automatically my mother handed me F equals ma. But that is not as simple as the story goes. F equals ma is an incredibly complex equation because it's a vector equation, and vector equations has at least three components. And if you want to formulate string theory with F equals ma, you're in deep waters. So no, F equals ma is good for the uninitiated. If you're not three kid, if you have a kid of your own, and then F equals ma at the first, right? They kind of say ma or something like that, and then F equals ma. And because F equals ma, see? Well, I would put in these forms from that. But anyway, so F equals ma is incredibly complicated. He confused the applications at that time as well. Newton was incredibly smart for everyone else. So they formulated their own version. So this is another version of classical. So that's the Hamiltonian formalism. Why do we need it? Well, you can use Lagrangian formulation and quantizer theory. That's fine. But that requires high brilliance. And we can all attest we are not as smart. No one, including me and everyone else, no one is as smart as Richard Feynman. So Lagrangian mechanics, when you try to quantize it, you need to go to path integral and all of that. But we won't really do that. The easier way is to learn about Hamiltonian formalism, which is another equivalent formalism of classical mechanics. And we learn that and we try and quantize the Hamiltonian formalism. That's way easier. It's less elegant, but way easier. All right. So given a field, right, you have a scalar field, phi hat, we define the momentum or conjugate momentum to phi. So does anyone know what conjugate means? Conjugate to phi. So what does conjugate momentum mean? Anyone? Everyone understands, like, who has had a course in classical mechanics? The real classical mechanics, not physics 111 or not the engineering or the real one. Okay. So then, what does phi mean? This capital phi. Conjugate momentum accept. What does it mean to be conjugate? A variable is a conjugate variable. What does that mean? Good. Yes, they're related in a sense that this conjugate phi is related to phi. Phi, you can replace it with the x in classical mechanics, and phi is just the momentum of whatever is moving. There, phi and x are related in the sense that once you measure x, you automatically kind of delocalize p. So they're related. They're not independent variables. So that's what it means, conjugated variables, right? Okay. So having done the terminology, now let's define what phi is. Phi, defined with the Lagrangian, is going to be the partial derivative of L with respect to phi dot. Remember again, dots on top means a time derivative of the scalar field. All right. So this leads to the Hamiltonian density. Again, we're discussing densities again. So this is the script H is a Hamiltonian density, and the Hamiltonian density is defined as follows. So you have pi I of x, you have phi dot I of x minus the Lagrangian. So this quantity here is the Hamiltonian density. Can anyone guess what the Hamiltonian is then? The integral, right? So then this is the Hamiltonian density, and then the Hamiltonian is simply the spatial integral of the Hamiltonian density. Okay. Now again, I'm going to abuse notation. I'm going to say many times, I'm going to say the script H is going to be Hamiltonian. Yeah. If you talk to a mathematician, make sure you tell them Hamiltonian density. Otherwise, things may get problems. Okay. So then, you have a real scalar field, Lagrangian, right? We have known this Lagrangian before. So I'm now, I think, considering massless scalar field. So there's no mass character. So this is the kinetic term spread out in basically separated out in time derivatives and the spatial derivatives. So that from this you can define a conjugate momentum, right? Conjugate momentum, remember, this is the partial derivative of L with respect to phi dot. So this is phi dot right here. So this is automatically set to 0 when you define a momentum. So you won't end up with this component, which is take the derivative, it's just phi dot. So this is conjugate momentum, and Hamilton's equation of motion is defined as follows. Similar to Euler-Lagrange equations, Hamilton has his own equation. So you have all these guys in the 17th or 18th century having their own equations with their need. And if you don't visit their graves, they will have their equations and breakdown. So the goal of everyone's life in this conference room should be to have an equation figured. So I don't get it. You have the chance to skip that. And I'm also older, so maybe I'll die first. Okay, things are getting hard. Okay. Now, so this is the conjugated momentum, and you can write on Hamilton's equations of motion. So Hamilton's equations are defined in terms of angularly the Hamiltonian, not the Hamiltonian density. So basically, phi dot is a partial h over partial pi, and the second equation is phi dot is minus partial h over partial pi. Okay, so these are the set of Hamilton's equations. These are the analogous version of Euler-Lagrange equation in Lagrange form. Right. Now, the first step to fetch for you that I believe is verify that the equation of motion for the free scalar field matches Euler's and Hamilton's formulation. So remember, you can write down any equation you like, but it must match up with any previous formulation that you're kind of elevating to your new equation. So then Hamilton and Lagrange formulation must match Newton's law. And they do. And I want you to verify that at least Lagrange equation and Hamiltonian equation has to be right. All right. Okay, this was I missed. All right, sorry. I was there for 3 years. All right, now get on to quantization. What is quantization? So basically, we have a free field theory in a classical setting. We need to elevate to quantum field theory. So we want to quantize it, right? So that's the first step. We want to canonically quantize it. Canonical quantization means that we're going to use Hamilton's equations and quantize it, or Hamiltonian formalism and quantize it. So we're dealing with Hamiltonians and whatnot. There's another quantization, the path integral quantization, which you'd use the Lagrangian formalism for. So there are two different quantization routes that you can follow in field theory. We're going the route of the canonical quantization. Correct. So the first step is you elevate your phi's, and h, Hamiltonians, with two operator that is stuck, right? So these are now operators that act on Hilbert space. Now, if you're very if you're going to be very specific about this, in field theory, we don't really have the Hilbert space. We have what we call a Fock space. So a Fock space is basically, what is a Hilbert space? Basically, you have quantum operators. Okay, I don't know what happened. The world is breaking. All right, can you fast forward to the last slide? So time can go back. Wow. Wow. I did a lot of stuff. All right. Yeah. Okay. Thank you. All right. So essentially, what is a Hilbert space? Hilbert space is where states so operators are defined on the Hilbert space. So you have a state vector that has its home in the Hilbert space. The operators act on vectors on the Hilbert space. That's what quantum mechanics works, right? These are abstract space we're talking about. These are not, you go into a room and we find it to be Hilbert space. It's not like that. It's very abstract. But in quantum field theory, we actually have a infinite number of degrees of freedom, one for each point in space-time. That means we are actually talking about an infinite Hilbert space, and basically the sum of all Hilbert spaces for individual points in space-time. So then we have this sum of Hilbert spaces, which is officially known as the Fock space. Okay, so that's very technical. But okay, you don't need it. Just consider it Hilbert space for now. So, okay, we elevate these things to operators acting on Hilbert space. And then what happens? The mouse stops working. Okay, now. All right. Now, recall the commutation relations from QM. So things are getting a bit technical now. So you have commutation relations, Q with QJ, QI with QJ, PI with PJ, that is 0. So we say that QI and QJ, let's say that, X, so QI is X, QJ is Y. So basically you're measuring positions of X in the X-axis and the Y-axis. And P sub I is then the momentum in the X-axis, the momentum in the Y-axis. If you measure them together, you get 0. What does that mean? Well, it means that what you measure first does not really matter because one does not affect the other, right? So if you measure the position along the X and then you measure position along the Y, that's exactly equivalent to what you had if you measure Y first and then X. Right? It doesn't, the order of the measurements should not give you different results. That's what it means for two operators to commute. Now, things don't commute. Those are, for example, this relationship, QI PJ is I delta IJ. Now, for the people who are actually closely relating and remember their quantum mechanics, they know that this is actually not complete. There has to be an H bar. But remember, we have set the H bar to 1. Pretty lazy. So then this has the H bar hidden. So don't lose your, don't go in a tantrum for H bar. The H bar is there, but set to 1. So this means that whenever you want I and J, whenever they're unequal, so you want to measure position along the X-axis and momentum along Y-axis, the order of the measurements doesn't matter. However, if you want to measure X and momentum along the X, then you get a non-zero commutation relation. That means if you measure very precisely what X is, the location, you lose the preciseness in momentum. So that's where the Heisenberg uncertainty principle comes in. So it matters the order of measurement. All right. So similar relations also arise in QFT. You have two fields commuting to 0 at X and Y at different space locations, and two consecutive momentum at different X and Y compute. And however, when you have same X and in same phi and pi same spatial locations, they don't go in a similar manner to quantum mechanics. Okay. But here, in case of the connector delta, you have a delta function because we're talking about a field spreading out, and this is a continuous variable. So connector delta is a discrete delta. Delta function is basically the continuous analog to the connector delta. All right, now these commutators, you will see that they are only dependent on the spatial coordinates, so they are taken at equal times. We call them equal time commutation relationships. So basically, measurements made at exactly the same time. Right? But now, a quantum field, now we're defining a quantum field, is an operator value function of space subject to the above commutation relationships. So basically, you have a quantum field, which is then a function of some operator. Okay? And technical aside here, I should have probably put it first, but the commutator, this square bracket of two quantities with a separated by a comma, is defined mathematically as AB minus BA. And this is like a group theory term. This forms algebra, Lie algebra. Okay? And we don't really have time to go over it, but that actually is a principle on which particle physics stands up, Lie algebra. Correct. So this is how you define a commutator of A and B. So A, comma B is AB minus BA. So this is 0 when the order doesn't matter. AB is exactly equal to DA. It is not 0 when the order is actually equal. Right? Okay. So then what next? Well, we want to determine the spectrum of the Hamiltonian. So what is the Hamiltonian ring? The Hamiltonian is nothing but, very crudely speaking, it's just the total energy of the system, the kinetic plus the potential. And so in quantum mechanics, we know that, energy for a harmonic oscillator, let's say, out with discrete levels. So basically, you say that it's a spectrum of an X. Or if you had ever studied hydrogen atom, they give you spectral lines. So that's where the word spectrum comes from. So different energies. So we want to find the spectrum of the Hamiltonic. That's what we mean. We want to find the energies of the theory. But that's not so easy in quantum theory because again, we are dealing with infinite space. So we're dealing with infinite number of degrees of freedom, right? So that's 3 spatial dimensions is hard enough, but then there are infinite degrees of freedom. If you have, but let us have to do it anyway. So that's why you're here in this fine morning. Right? Let's do it. Right now, let's solve it. The trick that people using QFT, it is the trick of Fourier transform. So everyone has Fourier transform in their repertoire. Fourier transform is basically a change in relation. So you describe the same physical phenomena in 2 different perspectives. Either you can talk about the position aspect of it, talk about fields as a function of position, but then also you can describe the field as in momentum space. That's, you go between the 2 descriptions, you use what we call the Fourier transform. That's defined as follows. So the phi of xt, spatial basis, take it to the momentum basis through this definition. This is nothing but the Fourier transform. This is pretty important, so you should write it down somewhere. And this is going to show up an infinite number of times during whenever you want to do quantum field theory. Not here, you don't have infinite time, so this would be finite. But in your life, you will do infinitely many Fourier transforms. All right, now, which this satisfies. So if now this is nothing but the expression for the scalar field, right? So you take the scalar field, transform it, move it to now phi is a function of p rather than x. So if you do that, then you plug into your Klein-Gordon equation. So did I define what a Klein-Gordon equation is? I did, but I just didn't mention. The scalar field equation is officially known as Klein-Gordon equation. So that is KG for short. Yeah, I'm producing my freedom. Yeah. KG equation. But you know what the funny thing is about the Klein-Gordon equation? I'm going off from tangents, but the history of physics is fascinating. And those who are not interested in the history of physics are really should not be interested in physics at all. Because the history of the Klein-Gordon equation is, Klein and Gordon are 2 separate people. So they came to this equation in independent. I think they're 2 separate. Right? So, and then, however, that's all the Klein-Gordon equation, but it almost got named to be Schrodinger equation. You know why? Because Schrodinger was attempting to develop quantum mechanics and then marry it to special relativity. And what he came up with was this Klein-Gordon equation. But he was talking about the Klein-Gordon equation for one wave function. But one wave function Klein-Gordon equation runs into all sorts of problems that we talked about before. Negative probabilities and whatnot, negative energy states. He did not know how to explain it. So he basically abandoned that idea and developed his own Schrodinger equation, which looks quite similar to the Klein-Gordon equation, but that's defined for one wave function. Right? But so it almost got named as the Schrodinger equation, but actually funny things happen. Things get named differently, will lead to different misstables. So then this satisfied, if you put it into this Klein-Gordon equation, the scalar field equation, you put this expression in, you will find that this satisfies your Klein-Gordon equation. Basically, you end up with a 0 for that. And after you've done all the calculation, after the dust has settled, the upshot is you end up with this equation, the new basis. So this equation was in the x basis, and this equation is in the p basis. So there are different descriptions of the same exact equation, one to the different basis, right? So this is the Klein-Gordon equation in the new basis that we're defining through this Fourier transform. So you separate it out. The upshot is, you see this was very familiar. You have a double derivative on the left-hand side with respect to time, and you have the field on the right-hand side multiplying with some constants. What is that? Harmonic oscillator. So what is that mean? So remember, this is the field, and field gives you the harmonic oscillator equation. So what is that? What can that physically mean? What is the physics of field or harmonic oscillator? Almost. What's more correct to say is that in every point on that blanket, you have a harmonic oscillator attached to each position in space-time. So these vibrate, and the vibrations in different modes give you what we call harmonics. Okay? So this is the meaning of the Klein-Gordon equation in the momentum basis gives you the log SHO for a simple harmonic oscillator. All right. And thus for each momenta, we have harmonic oscillator described by phi A of t. But how many of these do we have then? Infinite. But space is infinite, then momentum is also infinite, right? So that you have an infinite amount of harmonic oscillators described with fields, right? So each after frequency, t squared plus m squared root this expression. Now, your goal, second exercise, if anyone cares to do it, would be to actually do this just set it thing. Convince yourself that phi of x t written out in this Fourier transform actually reproduces this equation, right? If you are a student in my class, it will be tired of doing homework. So that's the, but yeah, so you're not students in my class per se, but the school students could it. So again, exercise, verify this, plus 10 points to do it. I don't know what you will do with those plus 10 points, but yes, plus 10 points for Gryffindor. All right, now, so simple harmonic oscillator seems important, right? So let's talk about this. My head hurts. Let me read. Oh, okay. So in quantum mechanics, what do we have? So let's remind ourselves, we have this Hamiltonian, right? So this is the Hamiltonian for the harmonic oscillator. I'm assuming a lot of things. I'm assuming that you have seen what a Hamiltonian is and you have seen harmonic oscillator. And basically, this is what the Hamiltonian looks like if you express the kinetic energy in momenta and the potential energy, its terms of position. So this is what the Hamiltonian for harmonic oscillator means. Okay. Now, communication relation that this satisfies, this P and Q is, we are seeing, is I. They don't commute, right? So it's a one-dimensional harmonic oscillator. So there's only one big, like x position and x momenta. So then they don't commute. So you have to, the order of the measurement matters. And you define something that is a dagger. What is an a dagger? Have you read Griffiths? Quantum Mechanics by Griffiths. Griffiths called these ladder operators. Okay. And I call these, in quantum field theory, it's called creation and annihilation operators. You can call them whatever, but they're the exactly same thing. Basically, you just define these variables in terms of the variables in the Hamiltonian. So a dagger has a minus sign in front of the p part, and this is the creation operator. And a is the annihilation operator. It has a plus in front of the p term, right? And these are complex valued. All right. So then from this, we can get a lot of things. We can actually rearrange these A daggers and A's, do some algebra, plus add the two, subtract the two, you get expressions for Q and P in terms of the creation and annihilation operators, right? That's algebra that my 2-year-old cousin can do. So yeah, you all can do it. I can do it, right? So then we can express Q and P in terms of A and A dagger. And the important thing is you find that the commutation relationship that A and A dagger satisfy is this. So again, A and A dagger do not commute. The commutation result is 1. So again, which one you apply, A dagger or A, first matters. Okay. And becomes 1 because you have I here and you take the product of A and A dagger, you have 2 I's. So basically you get rid of the I. And it's important that your A and A dagger commute to 1. Okay. So now you express your Hamiltonian, you do some more. So it's basically algebra. It's nothing new. So anyone who has not seen quantum mechanics can still do quantum mechanics if you have taken class 1 or grade 1 level algebra. Just play around with the variables. And you can define the Hamiltonian in terms of your creation or annihilation or ladder operators, A and A dagger. That looks very simple, right? So this expression right here is aesthetically pleasing than this one right there, at least to me, because this is much simpler. I'm pretty lazy, as I said. Haven't mentioned it before. I did. And so this is very short to write down. It's very, and then you can also work out the commutation relationship between H and A dagger. That comes out to be omega and dagger, and H and A, which comes out with a negative sign in front, omega times A. And all this basically leads to the following. You're basically going to define the energy eigenratios. So we have moved First, remember we moved to the PQ Hamiltonian in terms of P and Q. And then the Hamiltonian, it is not really the P and Q, moment and position are not really eigenstates of the Hamiltonian, but the energy is the eigenstate of the Hamiltonian. So basically, we're moving, when we defined H in terms of A dagger and A, we actually move to energy basis. Okay. And so this is an eigenvalue equation. The state remains unchanged under the operation of the eigenvector. The operator. And then you get the eigenvalue associated with the eigenvector. So E is the eigenvector, E is the energy eigenvalue, right? So if you have, let's say, energy level 1, so this will stay 1 in both sides. And the corresponding energy, the first level, let's say, is H bar omega or something. So that would be the energy corresponding to the level 1. That's how you interpret it. Okay? But that's, don't take this to the bank. It's just an assumption. All right. So from this, then, we can construct the ladder states. What does that mean? Well, we have our spectrum, energy states. You basically create particles, you go up, you destroy particles, you go down the ladder. So we call this the ladder state of energies. Okay, so in this manner. So if you act A dagger to the right of H and then tag along an eigenvector E in it, so we basically an energy eigenstate. Basically, what happens to this eigenstate is this X on E increases the eigenvalue by omega. Okay, and this is what you get. And if you do the other one, you act with this annihilation operator. You act with an A, you get a decrease in the energy by omega by the same amount. You increase by the same amount, you decrease by the same amount. All right. All right. Now, these populate the energy eigenvalues, right? So you basically have states of energies, which you can go up and down using A daggers and A. So the ground state energy of a harmonic oscillator, if you keep acting on the eigenstate, if it's operators, say an A dagger, what you find is the energy is bounded below. That means the energy has a starting limit. You can't go lower than that, but you can go very high, right? So it's energy below. It's a bounded below, and the ground state or the lowest energy state is defined by a 0, and the eigenvalue is H bar omega over 2. But remember, H bar is set to 1, so it's omega over 2. And then starting from that ground state, you can act your ladder operators, the gradation operators. What will they do? Well, they will keep increasing omega by some fact, right? A constant. So you keep going up a stage every time you act A dagger. So if you act A dagger n times, you get the n eigenstate, or the act A dagger on the 0th state. And the eigenvalue equation is that H on n is the eigenstate, gives you the eigenvalue n plus 1/2. So every time you act with A dagger, you get 1/2 added to it. Okay? All right. So then the ladder states, if you plot it out for a harmonic oscillator, looks very nice. Looks like this. So this is the ground state of energy 1/2 H bar omega. Again, not from a field theory book. So H bar omega is there. H bar is still there. But remember, H bar is 1 for us. And if you go to L equals 1, you gain a half of the energy. 1 plus 1/2 of the energy. So 3/2, right? And then you keep going by steps of 1. That's the spectrum of the harmonic oscillator in quantum mechanics. It's not even field theory at this point. So what I want you to do is verify the expressions for these commutation relationships just by things in algebra. Remember, you don't need training in quantum mechanics to do this. It's just algebra. All right. So at this point, this was supposed to be the end of lecture 1, but it wasn't. But I will stop for a question. Any question at this point? All right, good. Okay. Now, lecture 2. Okay. Lecture 2 is just start. Oh, I missed some. All right. So now the Klein-Gordon equation, let's recast it in the momentum basis. Let's revisit the Klein-Gordon equations. we found this, right? So we found this in the few slides ago, this harmonic oscillator thing, and we realized that this is a harmonic oscillator with frequency that much. And this tells us that when we have a field, you put harmonic oscillators and stack it on top of each spatial space-time point, you get an infinite amount of harmonic oscillators. So basically, this free scalar field is nothing but a collection of harmonic oscillators, one for each point in space-time. And the general solution to this is then written as an integral, basically because you're summing over all these harmonic oscillators. A continuous sum is then an integral. So it's integrated over the momentum space, because remember this is on the momentum basis. So this is the 3 integral over momentum. And 2 pi factors come in from the Fourier transform definition. And we're expressing it in terms of the creation and annihilation operator. Right. And elevating quantum mechanics to quantum field theory then finally means that your A and A dagger plus 1 in quantum mechanics. But then you have A and B dagger for each specific momentum, right? So then you can define for each specific momentum, A K and A dagger, P. So based in the combination relationship for P theory. Essentially what that means is that everywhere they commute apart from K and P, right? Apart at K and P, something weird happens in the Bell function that goes up when they're 0, when K and P are equal, right? So this is the commutative relationship that gets changed. This is from quantum mechanics. This is quantum field theory. And A dagger acting on the 0th state is defined as giving you the 1 over square root of 2 omega p of this p state. This basically creates particle with momentum p. So A dagger acting on 0 will give you the next state, which is something with momentum p. And this is the constant attached to it. And this leads to define the phi of xt in this manner. So basically, what happens is you tack on 0 gear and you get stakes of p. So you get an extra factor that is this one. And we are now combining. You can see that p doesn't have an arrow on top, p dot x. Now they have an arrow on top. And essentially the signs have kind of flipped over. Now this is a minus and this is a plus. Why is that? Do you think, why that is? Essentially, any letter which is supposed to be a vector is written with a vector on top, means that you're talking about Euclidean spatial vectors or Euclidean vectors, 3 variables. But any vector that is supposed to be a vector, you're not writing with a vector on top, is a space-time vector. So you don't need, so basically the sign changes because remember the metric, there is a minus, relative minus sign leaving the spatial sign coordinates. So when you move to this picture, there's the minus signs both. All right. So once you have defined the field in terms of the ladder operators, you can then go ahead and define your conjugate momentum. Conjugate momentum is phi dot of xt. So you take the time derivative of this big thing, and this is what you end up with. Okay. All right. So these probably are important expressions to remember. So we have defined phi, we have defined pi, the conjugate momentum and the field, scalar field in terms of ladder operators. So if you plug all these expressions for pi and phi into the Hamiltonian assumes the form that looks like, so this is the definition of the Hamiltonian. Now you start plugging things in. After all of the algebra is done, it looks like this, very compact form. So basically, you're expressing your Hamiltonian in terms of the momentum integral over 3 space, and it's basically a sum of harmonic oscillator space. Okay, basically A's and A daggers. So what do you think happens if you act this Hamiltonian on the ground state? Well, somewhere it creates particles, somewhere it destroys particles, right? Simple enough. So that's where particles come from. So, but before we go into particles, let's do something. Let's expand this out. If you expand this out, you get 2 terms, right? And you get this piece right here, you get this piece right here. Now, discuss anything look troubling to you at this point? Right, good. People are alive. Well, okay, so this term here is alarming. Why is it alarming? As he said very correctly, we have infinity working around here. What is the infinity? Well, obvious infinity is this, right? Delta function at zero is blown up to infinity. So that's the obvious one. Actually, there are two infinities lurking around. So this curve is alarming, and quantum field theory is riddled with these infinities. Okay? And in fact, in this two terms, in this one term, there are two infinities. One is pretty obvious, right? It's the delta function infinity. And we want to analyze them. So let's analyze the infinities. So we trap particle in a box. So there's a box and there's a particle inside. The box is outlined well. And delta 3, the 3 just means it's three-dimensional delta function of 0 just means that this integral is, you make it into an improper integral with the limit goes to infinity, limit of the length goes to infinity, and you basically integrate over the length of the box, right? Essentially, you get the volume if you have three-dimensional integration. All right. So once you do that, what do you get? Well, at p equals 0, this is what you have remaining. Why is p equals 0? Basically, you're localizing the particle. So basically, you're making the momentum intercept. So let's say p equals 0. And then we're basically telling that particle is forced to be at rest or something like that. And then, so this integral is, of course, going to be infinite because space is infinite. So the volume that this integrates to must be infinite. So this is the obvious infinity. And this is related to the spatial infinities, that the fact that the space itself is so large that it's infinite. So the volume integral is an infinite number. So this is known as the large distance or infrared divergence. This is not so troublesome. These are quite easy to deal with, as we'll see. However, one thing that is not obvious from this integral is this integration right here. We have gone from, to do this, we localize the particle. So we have gone from the p integral to the x integral here. And we have seen the volume integral goes to infinity. That's fine. That's due to the infinity of space. However, this integral measure of over 3 momentum of this quantity is also infinite, because if you integrate over all of momentum, there is no limit to how big the momentum can be in space-time. So then this integral, you integrate over all of momentum, basically you sum over all the momentum, it blows up to infinity as well. Now this was less obvious. And this arises due to the nice assumption that quantum field theory is valid to arbitrarily high energy. And remember, energy mass equivalence means that energy and momentum are on equal footing in space, being a space platter, right? So basically, if QFT is valid to high energy, all energy scales, like up to the Planck scale or something like that, then this leads to infinity. So this tells me that quantum field theory cannot be valid to all energies, arbitrarily high energies. They have to cut it off somewhere. So what we do is do exactly that. High energy corresponds to very small distances. Remember, the Planck energy is incredibly big, 10 to the 90 GeV. So the Planck scale or the Planck length is incredibly small, 10 to the minus 35 centimeters or something like that, right? So then what we have to do is then we tackle this by introducing a cutoff energy scale. So this is called the high scale cutoff. So for any quantum field theory that you write down, you always have to define energy, the high energy at which it stops being valid. Right? Beyond this, we don't know how to deal with the infinity. So this is known as short distance or ultraviolet divergence, this kind of infinity. Right? So infinity is over momenta, is ultraviolet divergence because of the short distance nature of phase that we're looking at. And the spatial infinities are large distance. Right? Space integrates, the volume integrates to infinity. That's infrared divergence. All right. Now, so that's problematic because this is also problematic. I've left many things unanimated. That's not nice. It's giving me an OCD. All right. Anyways, so that what we do, the Hamiltonian had two terms. But basically, what we do is we define a cutoff energy beyond which our theory is not valid, and we end up with just this part of the Hamiltonian, just the one that is nice. That's the one that is not infinite. So this is the term that we end up with. And you notice these two columns on either side of H. What does that mean? Well, this just means it's normal order Hamiltonian. Normal order means that if you apply this Hamiltonian on the round state, you get 0. So then you start from a finite state, you up, and then you go. So normal ordering will always have the annihilation operators acting farthest to the right. That's normal ordering. So normal order operators are nice. When operators are not normal, they can give rise to infinity, as we are seeing. Right. Now, the relationships of H and A dagger, you commute, you get this omega PA dagger. And with A, you get a relative minus sign. This still holds, right? For this Hamiltonian, this still holds. So our theory doesn't need to be modified too much. It's still working. So then how does this work? Well, you start with your commutation relation, H with A, and you expand it out. And basically, H and J is just state A minus AH acting on some state alpha, some random arbitrary state alpha. And you basically do this thing. A first acts on alpha for this term. H first acts on alpha for this term, right? And then this thing is just going to give you the eigenvalue equation because these are energy eigenstates. Hamiltonian acting on the energy eigenstates spits out the energy value, right? Energy eigenvalue. So you get omega alpha. Omega alpha are the energy eigenvalues. And alpha is the energy eigenstate. Now, what you end up, this is equal to this result right here, minus omega PA, right? Now we do some algebra again. We do some rearrangements. We want to know what this term is, H, A, alpha. You rearrange it, you get omega alpha minus omega P, or A with acting on alpha. So this is a new state with energy omega alpha minus omega P. So what we have ended up doing is we have formed a Hilbert space with state vectors. It's starting with 0, and then we move to a new state, let's say P, and then you act it. This is the one particle state, and you can find the energy of this because of the Einstein energy relationship, and then you can get to two particle state. You get the energy gets added up. One has momentum P, one has momentum Q, and you can do it for many particle systems, right? So this is just by doing. You go from the ground state, you keep acting the ladder operators on your H, on your eigenstates, and you end up with this kind of spectrum. Right. Now, what does particle statistics have to do with that thing? Well, you realize that A dagger Q acting on 0 will give you a new particle state with Q momentum, and A dagger P will give you a corresponding state to P. So this is a two particle state. This is how two particle states compound. So if you have multi-particle system, then you have multiple ladder operators individually for each particle. All right. So AQ will never give rise to P. A dagger Q can only give rise to Q momentum particle. Right. So similarly, you change the order, you get particle state which is QP, but this PQ and QP are exactly the same under interchange, and this is Bose-Einstein statistics. And why is this valid? Why is this two equal? Because remember what we're talking about really. We're talking about phi. Phi is the scalar field. And scalars are, if you're well versed in some aspect of quantum mechanics or statistical mechanics, scalars are spin zero particles. Spin zero particles are what we call bosons. And bosons obey Bose-Einstein statistics. So this kind of a spectrum will follow this statistic even under interchange. All right. So this is basically turning out to be the quantum field theory for numerous spin zero bosons. So this is how particles are arising. We're basically acting creation and annihilation operators of the harmonic oscillator for each individual points in space-time basically acts and gives you new states. So that's where particles come from. So in quantum mechanics, we know that P and X are not normalizable. Why is that? So there is no limit to x and t. They can go up to the delta function. So they're not normalizable. And in QFT, same kind of argument holds for phi and AP, because we just have then this delta function, this continuous delta function. All right. So basically, you have 0. You act with the A dagger on 0. You get a new state P, and you basically annihilate a 0, and you get this P and P, and this normalizes to the delta function. And if you're talking about scalar P, then phi sandwiched in between two ground states gives you x and x, and this gives you delta 0. So you see delta 0, delta 0. So these blow up to infinity. So they're not heights. So phi and AP are not, phi and phi are not actually very nice operators. Very nice things to normalize your field theory in. All right. So that we define a constraint on our field theory, we always be Lorentz invariance. So we want whatever field theory we make up, we want it to be whatever equations are, we want it to be Lorentz invariance. Right. So first, we define Lorentz invariant one particle state as this piece right here. So basically, you act with your ladder operator on the ground state, you get a new state back. Right. So that's a Lorentz invariant state. This guarantees Lorentz invariant, this factor right here. And this satisfies the normalization condition that you have two different states, P and Q. The product, the inner product of this turns out to be some constant that is due to Lorentz invariance, and some of this piece right here, which looks hell of a lot like this thing. And so we know that this thing blows up, right? So this thing goes to delta 0. However, you can always do some algebra. So remember, the product of two operators can always be related to the commutation relationship. So A and A data will always have a commutation relationship. So what you can do is basically rearrange this, manipulate this term, and separate out into two terms related to the commutation relations for these operators, right? And you realize this term right here, A, mixes up annihilation operators. What happens when you annihilate the ground state? You get 0. You don't get anything below 0. That's the lower limit, right? So this goes to 0. So this term completely goes away. All you're left with is then this term. We already know what the commutation relationship is, this state. So this comes out to be the normalization of P and Q. Right? So we are saying as long as P and Q are not the same states. All right? So they're not the same momentum. So P forms a complete set of states such that it has a completeness relation attached to it. Basically, if you integrate over all of the P's and take the outer product of the state vectors, you get the identity. That's the completeness relationship elevated to field theory. In quantum mechanics, you just have some integral P equals 1. But then you have all these different Lorentz invariant factors in QST. All right? And these are the distributions, not functions, because remember, we're actually describing functionals of space. And we can construct well-defined operators by a linear superposition of plane weights. So essentially, we're describing the excitation of the fields by plane weights, because that's how things work out. So this file X active on 0 gives you this state. This is going to be interpreted as phi X acting on 0 gives you a P with some of these factors in. So essentially what it boils down to is that you're creating some new particle P with the scalar field, right? So basically phi X is breaking a particle at position X. How long do we? Negative? Oh, so it's okay. So sorry. I think I can stop here. Yeah. Okay. So this is where I stop my second lecture. Questions? I really enjoyed it. Ran out of time. So questions.